In Module 2, we'll now turn to the log-normal distribution. And we saw the log-normal distribution appear in Chapter 11 as we were developing the binomial lattice structures and investigating properties of that and thinking about what kind of model of security prices that lattice represented. So we're going to dig in a little more deeply into some of that work here in subsequent modules. First of all, the definition. What does it mean that a random variable is log normal? Well, basically, there's a couple of ways of saying it. One is that if the log of y, so here y is the random variable that we're saying, and sometimes you'll see the notation ln, and then we'll give a mean and a variance, say m and v squared. This book does not use this notation ln for log normal, but it's common in many applications. So here we're saying y is a log normal random variable. What does that mean? Well, it means that if the log of y is x and x is normal, that's what it means. So y is log normal if the log of y is normal. Another way of thinking about it is this way, namely that a log normal random variable is an exponentiated normal. So the relationship of moments is identical. In other words, if y is log normal, and in either one of these statements, x is normal with the same moments, m and v squared. So if I take a normal x with moments m, v squared, and exponentiate it, that becomes a log normal with parameters m and v squared. I can't say mean and variance. It's important to note that for the normal x, m and v squared are in its mean and variance. In the log normal distribution, that m and v squared are parameters that define the distribution. They are not the mean and the variance of the log normal variable. Important to keep that in mind. But they're parameters that define it. We'll see what the mean and the variance of the log normal are in a few minutes, and we'll see they in fact involve the m and the v squared, but they are not equal to m and v squared. But it's common to identify the parameters of the log normal as the parameters of the normal that give rise to that log normal. So again, y is log normal if the log of y is normal, or if y is equal to an exponentiated normal. Just two ways of saying the same thing. And the most common application for our purposes are the case where we have continuously distributed returns in our stock model. So we say that st is equal to s0 e to the xt, and we might assume that xt, the continuously distributed return for the period 0t, that we might assume xt is normal. So not surprisingly, we'll see it in more detail as we go through, that this is the classic example for our applications of a log normal distribution. Namely, st is going to be log normally distributed because it's related to an exponentiated normal distribution. And it's common to assume that the continuous returns are normally distributed. So let's look into that a little bit more detail. So here we're assuming we have continuously compounded stock returns. And as a refinement of the earlier equation, here we'll think of, perhaps as you might think of a lattice where sequentially we go from S0 to an S value at time delta t. From there we go from to an S value at time 2 delta t and 3 delta t and so forth. So here is just an iterative formula where we basically say that at time n delta t, the stock value is equal to the stock value one period earlier, namely at time n minus 1 delta t. times e to a return. And in this model, we assume that the xn, the return in each one of our periods, is normally distributed. Notice it has the same parameters. We're assuming that our normal distribution has the same mean and variance in each time interval as we move through time. Also note that, and this is common, we'll see this in a little more detail in a minute, that here we're explicitly saying that the mean and the variance of the return are both proportional to the interval of time. So this statement, there's a lot of information in this couple of mathematical expressions. One is the assumption of normality of each of our period returns. The second is the assumption that the parameters of that normal distribution are the same, they're constant in time. The third is that both the mean and the variance are proportional to the time interval length. As delta t gets longer or shorter, the mean and the variance scale proportionally. Notice it's mean and variance that are proportional, not mean and standard deviation. Finally, we're also going to ultimately be assuming that these xn's are in fact independent. So if we have a time capital T, which happens to be n steps, n delta t steps, so we get the time capital T, st is just s0 e to the x, right? You just multiply, add up the exponents, and now we use a property that we've seen earlier, namely that if each one of these x's is in fact normal, then the sum is normal, and the mean of the sum is just the sum of the means. So if I take n times mu delta t, I get mu capital T. And notice here I'm assuming independence, because the variance of a sum of normal variables is not just a simple sum of variances. There's covariance terms in there. So we're explicitly assuming, as we go to this next step, that we have independent returns in each one of our successive periods. And that's why we get the sigma squared t. So this means st is log normal. And the reason is I simply take logs of both sides of the equations. What does it mean for st to be log normal? We just check with the log of st. So we take a log and we get this expression. We get the log of s0, which is a number, plus a random variable x. Well, if I add a number to a random variable, all I do is shift the mean, no variance shift. And we see then that the log of st has mean, log of s0 plus mu t has variance sigma squared t. So indeed, in this model of independent normal returns, the stock price at any time t in the future is normally distributed. Therefore, st, the stock price at any time in the future, is log normally distributed. And of course, the parameters of st involve more than mu and sigma squared. They have to involve the initial stock price.